Hey everyone, and welcome to The Explainer. Today we're diving deep into one of the most fundamental and, let's be honest, one of the most beautiful ideas in all of physics: what light actually is. This is a question that stumped scientists for centuries. Is light just a stream of little bullets, or is it some kind of ripple moving through space? Well, it turns out the answer was hiding in plain sight, tucked away in a set of equations that seemed to be about something else entirely. All right, so here's our game plan. We're going to start with the old rules of electricity and magnetism. Then we'll see the one tiny piece of the puzzle that was missing. After that, we'll watch as a wild prediction is born from the math. We'll dissect what that wave actually looks like, and finally, we'll talk about the energy it carries with it. So, to really get a handle on light, we actually need to rewind a bit and talk about the forces that create it. Back in the mid-1800s, physicists thought they had a pretty good grip on electricity and magnetism, but they saw them as two totally separate things. Okay, so rule number one, Gauss's law for electricity. And honestly, it's just so elegant. All it's really saying is that electric charges, things like protons and electrons, they create these invisible force fields around them called electric fields. It's that simple. Charge is where all electricity comes from. All right, now for the magnetic side of things. And this is where it gets a little weird. See that zero on the right side of the equation? Yeah, that zero is a huge deal. It's telling us that there's no such thing as a magnetic charge. You can never, ever have a North Pole all by itself without a South Pole attached. The field lines always have to loop back around. Okay, and this is where the magic happens. This is where these two forces really start talking to each other. Faraday's law was an absolute game changer. It proved that if you have a changing magnetic field, like, say, you're just wiggling a magnet around, you actually create an electric field out of thin air. This is how every electric generator works. So the key takeaway is a changing B field makes an E field. So we've got our rules, right? Charges make E fields, magnets always come in pairs, and changing B fields make E fields. But there was a catch, a big one. There was a deep mathematical contradiction hiding in the law that described how electric currents create magnetic fields. The law worked in most cases, but it was incomplete. It needed a fix. So on the left, you've got the original Ampere's law. Super simple, right? An electric current, I, creates a magnetic field. Easy enough. But a physicist named James Clerk Maxwell realized this couldn't be the whole story. So he added that little extra term you see on the right. It was a small change, but it was based on this revolutionary idea. What if a changing electric field could also create a magnetic field? It wasn't just fixing a math problem. It was changing physics forever. And this new term? Maxwell gave it a name, the displacement current. But here's the thing, and this is key. It's not a current like electrons flowing in a wire. It's way more abstract. It's the idea that a changing electric field, even in totally empty space, behaves as if it were a current, generating its own magnetic field. And just like that, everything clicked into place. Now it was perfectly symmetrical. A changing B field makes an E field, and a changing E field makes a B field. Okay, so with that one little tweak, Maxwell basically unified all of electricity and magnetism into one beautiful, complete theory. But buried inside these new, complete equations was a prediction so startling nobody saw it coming. Just think about that for a second. You've got this chain reaction, right? An oscillating electric field creates an oscillating magnetic field. That changing magnetic field then creates a new oscillating electric field, which makes a new magnetic field, and on and on and on. It's this incredible self-sustaining ripple that can just travel through the vacuum of space forever. It doesn't need anything to travel through because it just keeps making itself as it goes. But here's the real kicker. Maxwell realized he could actually calculate the speed of this thing. And its speed didn't depend on how you made it or how fast you shook the first charge. Nope, its speed depended only on two fundamental numbers that physicists already knew from completely separate experiments. One constant for magnetism, mu0, and one for electricity, epsilon0. So this is it, the equation for the speed of his theoretical wave. He just had to plug in the numbers that people had already measured in their labs. So he takes the known values for those two constants, plugs them in, and crunches the numbers. And what does he find?
He gets 300 million meters per second. And that number, that wasn't just some random speed. That was the exact measured speed of light. It was this incredible aha moment. Maxwell's electromagnetic wave was light. Suddenly, light wasn't some mysterious phenomenon anymore. It was a wave of pure electricity and magnetism traveling through the cosmos.
So, okay, Maxwell just blew everyone's minds, right? He proved that light is an electromagnetic wave and basically united two whole fields of physics. But what does this wave actually, look like? How does this thing dance its way through space? All right, so try to picture this. The wave is coming right at you. The electric field, the E, is bouncing up and down. As it does that, it creates the magnetic field, the B, which is oscillating left and right, completely at a right angle to the electric field. And get this, both of them are also perfectly perpendicular to the direction the wave is actually moving. They're locked together in this amazing three-dimensional dance. And the ratio of how strong they are is always fixed at one constant, the speed of light. Okay, so if light is a wave, a ripple in space-time, then it's got to carry energy, right? I mean, you feel the sun on your skin. That's energy being delivered from 93 million miles away. And the amazing thing is, Maxwell's equations let us pin down exactly how that works with incredible accuracy. So all the energy in a light wave is stored in its electric and magnetic fields. But what's really mind-blowing is how they share the load. It's a perfect 50-50 split. Always. At every single point in space and at every single moment in time, the amount of energy in the electric field is exactly equal to the amount of energy in the magnetic field. Perfectly balanced. So how do we actually track this flow of energy? Well, physicists have a tool for that, and it's called the Poynting vector, which we write as S. This really elegant little vector tells you two things. Its direction shows you which way the energy is flowing, and its size, or magnitude, tells you how much energy is flowing through an area per second. Basically, it's just a fancy way of describing the light's intensity or its brightness. And all of this leads to one final and honestly pretty profound idea. In physics, if something has energy, U, it also has momentum, P, which means light pushes. I know, it sounds crazy, but it literally exerts a tiny physical force on anything it hits. So that leaves us with one last question to chew on. We started with a few rules for electricity and magnets, and we ended up discovering that light itself is a force that can literally push things. So, if light has momentum, what could we push with it? Could we really build solar sails and travel the solar system on nothing but sunlight? The physics? Well, the physics says absolutely. What began as a simple correction to an equation turned into a blueprint for exploring the cosmos.